This work was funded by the ESiWACE2 project, which is also bringing us this this tutorial workshop. So thanks to them. It's one of the questions we get asked quite a bit is well, you've got all these different DSLs. Why have you got different ones? I think Carlos answered the question to some extent, but I think there is a need for different types of DSL. But one of the questions is there any way we can do some sort of interoperability between them? And this is some initial work to see whether or not there's a chance to do interoperability in this case between PSyclone and Dawn, which you'll be hearing about over the next 2.5 days. Oh, sorry, I thought there we go. Yeah, so you've seen this picture in various forms. Sergi showed this before, and you might have been wondering about this SIR thing down here, which we haven't talked about. I think we talked about all the others. So that's what I'm going to talk about. And so I should probably say what it is. So SIR stands for the Stencil Intermediate Representation, originally designed for representing structured meshes, and its provenance comes from Cosmo. It's being extended by Météo Suisse and others for unstructured meshes as well, and you'll hear all about that. So I'm not going to talk much about that, but you'll hear all about that in the over the next couple of days. But the thing to notice here is that, as you would have seen from Andy's tutorials, is NEMO has structured meshes and has stencils. So there's a chance that that we could be able to use the NEMO API here and maybe go and translate into this SIR representation. So if we're in the SIR representation, then as I said before, that feeds that is essentially the input to Dawn. And I apologize if I got the wrong name here. I think it is still called SIR. If it's not, then people can correct me in the afternoon and onwards. But essentially, there's this intermediate representation, which I'm calling SIR for the moment. It certainly used to be called that. And then that is input into Dawn, and then Dawn optimizes that and produces parallel code output in various flavors. Again, I'm not going to talk about those because you'll hear all about those in the next 2.5 days. But the point is we can now stick these two things together and get this rather nice picture here, which basically says we can start off potentially with some Fortran code, and we can take that in through our front end. It's called the NEMO front end, but as Jörg said, you know, there are other models, ROMs, for example, that might go through here as well. And then that gets translated into our internal representation. And then if we can translate that through our SIR backend into SIR, then we can then use Dawn to produce code this way. So there should be some route between essentially what is PSyclone here and then Dawn here. A couple of things I should mention about this as opportunities. One is you can just go straight through, like I said, Fortran code straight through, all the way through, and out you go. One thing that we could think of PSyclone as being is something that actually tidies up the code ready to do this translation, because there may be things in SIR well, there may be, sorry, put the other way around. There may be things in the SIR that are not represented in the SIR. So maybe some Fortran things. You've heard about having code blocks and things. There may be things that can't be taken through into the SIR. So one thing we can do is we can go from here into the SIR, and then we can do some transformations on the SIR to make it essentially suitable, pre-process it in some ways, and then make it so that it can go through here. Another one is if we have Fortran code or something that can't go through this way, maybe it's write statements and things like that, we can actually use our Fortran backend for that, and then we could then do SIR for a subset of the Fortran. So we could just target part of the code which goes through here as well. So this kind of gives quite a powerful, almost pre-processing stage to using SIR and Dawn. One interesting approach. Now, actually, I mean, whilst this is a really nice picture, this isn't such a nice picture. I don't think it looks as pretty, but it's the same thing. But I think this is probably a fairer view of the way I see things, or a better view. It's the same thing. So you've still got PSyclone front end, SIR goes through to the SIR and through Dawn. It's just showing you that really there are PSyclone front ends and there are SIR front ends, Dusk and others. And in theory, you could go the other way as well. And then there might be some reasons to do that. So it doesn't necessarily have to just be the one way. It could, in theory, the other way. It's dashed because we're not looking at that, but it could happen. So I won't dwell on this too much. This is just showing, you've been looking at some of the internal representation over the last couple of days of the SIR, and you will have seen assignment statements and array statements, binary operations, literals, things like NEMO loops and NEMO invoke schedules. So they're the things that are our nodes in our SIR, and this is just showing how they map to the Python API that's in the SIR. So there's some pretty much one-to-ones in some cases. So a binary operation has a make binary operator in this side. A literal and a unary operation has a make literal access. So there's some one-to-one mappings that make things relatively easy. And essentially what I implemented in the back end was take these sorts of nodes and translate those nodes into these sorts of nodes. And there's some where we have to expand and do other things as well. But basically, these are the main mappings that are in there that map from this to this. Okay, so let's just take an example. This is a very simple snippet of Fortran code, which does a Laplacian. Obviously, it's not got anything else in it, but it just serves an illustration. So if we take this as input to the PSyclone NEMO API, then we capture that in our internal representation. This is the view method showing our internal representation. Obviously, it's a lot longer than this. It's just a snippet of it. It carries on a lot further down, but you can see there's a Laplacian operation, ijk. It's got an add and multiply, etc. So that's our internal representation of this. And then if we apply our backend SIR to this, our backend then produces Python code, which is the Python SIR representation. We even put a little note saying it's done. And this gives us the same thing. There's a Laplacian. It has a stencil accesses and things like that. So this is just that translation to the SIR. So now once we've done that translation to the SIR, that can then be read in by Dawn. You can ask Dawn and say, please can you tell me what it looks like, and it presents you with a nice view of what it looks like. So you can now see we've got our Laplacians and our outs, and it's got the -4s, the same thing. So this is now in Dawn, ready to be optimized. And then we chose, I just arbitrarily chose one of the output options. I chose cuda, and then we can generate cuda code from all of this. And whilst obviously cuda's not the nicest of languages, you should see somewhere in here there's the Laplacian with some access. There's your -4 and other things in there which I can't see anymore. But anyway, so that's there. So that this shows us that this was automated. Essentially, all those steps can be done through. I say fully automated. Okay, there's a slight cut and pasting that needs to go on, but essentially the process is all the code generation part of it is fully automated through this. Well, that's a simple snippet of code, and we can do a number of simple snippets of code. Is relatively easy to do and seems to work okay. What we're working towards is trying to get the NEMO tracer advection benchmark working, which was the example you've been using in Andy's tutorials in NEMO of the last day and a half, and that was originally provided by CMCC. So thank you to those to them for that. I think, as Andy pointed out, it's also being used as the basis of the NEMO dwarf in the Escape2 project. So the NEMO dwarf will be very similar code to this. The actual code itself and where we're up to is just in one of our examples, NEMO EG4. So you can look at it anytime you like. As we do more to it, that gets updated. So if you want to look, it's openly available. Most of you who've done the tutorial know where I'm talking about. rather than going to /tutorials, you go to /examples. It's just there. And what I've done is I took the original NEMO trace reduction benchmark and then I commented out the bits that aren't working. So it's not going to run or anything. It's just the translation part. And the bits that aren't working at the moment are 1 and 2D arrays. The 3D arrays are fine to translate, but I just need to work out how to do 1 and 2D array translation. I just need to talk to the Dawn people and get that. I had some initial discussions, but just need to sort out how to do that. Another one is at the moment there are the implicit loops you would have seen, so they're the array notation essentially. We need to transform those into regular loops, and I'm working on doing that in order to go from the SIR to the SIR representation. We also have imperfectly nested loops in there. Some of you might have seen some things in that, and at the moment I don't quite know how to deal with that. Probably going to have to do a transformation which turns imperfectly nested loops into perfectly nested loops, I think. But there may be something in the SIR that allows us to do that. I don't know. And then there's just an internal issue, some bug to do with that -x. So if you're interested in seeing these things, you'll just see that they're all commented out, and there's all, the code is in these, and you'll see where we're missing things. Just that. One of the things we do already, and this is one of these examples where you can kind of use PSyclone as a kind of a pre-processor in some ways, is the trace reduction benchmark does have a number of Fortran intrinsics in it, sign, min, and abs, and possibly others, I can't remember. So at the moment, and it may be, or at least when I did it, the SIR didn't support these concepts. Now it might do now, but it didn't at the time. So what we do is we transform those from these intrinsics into the equivalent code. And if you've done some of the earlier tutorials, you would have remembered that we also changed a matrix multiply into code for another reason. It's just the same sort of transformation as that. You just say, when I find one of these things, please change it into code. And then that allows us to change the Fortran source in our SIR. Well, what was Fortran? Change the internal representation of it, and then it can go through into the SIR. So that helps with a lot of the code. And at the moment, where we're up to is transforming around 183 lines of Fortran code. Actually, that's a lie. That's the number of lines in the thing. It's probably more like about 100 lines of Fortran, and we're generating around just over 1,000 lines of Python SIR. So in summary, it looks like the SIR NEMO API maps quite well to SIR because they're essentially dealing with similar concepts, it is possible to translate from SIR to SIR, where the SIR supports it. And of course, jumping down, PSyclone is able to transform the code to help with that translation where it doesn't support it. And simple examples work. And we're working on this NEMO trace reduction benchmark, which of course is one routine inside NEMO. So we're kind of trying to look at how far we can expand this out into full NEMO, but I think if we get the NEMO trace reduction benchmark working, I'll be very happy. And I think that's it. Yes, thank you.